calculation. Suppose if you want to do for high pass, then we have to do our uh, transformation, frequency transformation using this formula, right? So if you want to do it with the band pass, then we have to, after finding your low pass filter calculation h of s, then we have to substitute your s value with this value, right? So here these are all the calculations, and similarly for low pass to band stop filter. So these equations are very helpful while transforming from the low pass to your analog other kinds of filters, right? So low pass to unnormalized to normalized one, and here this unnormalized low pass filter to normalized high pass filter, all these things. So no, right? So normalized in the sense omega c value is equal to 1 radian per second. If it is other than that value, then it is a unnormalized one. And for conversion from h of s into h of z, so from these procedures we can able to find our h of s only, right? So if these, that is the transfer function of our analog filter. So if you want to do your design in the analog domain, then you can stop at this point. But if you want to do your digital filter design, then we have to go for conversion, analog filter to digital filter, digital domain conversion. As we discussed, we are having three procedures: approximation of derivative. Here the h of s, in the h of s equation we have to replace wherever we are having s, that should be replaced by 1 minus z power minus 1 divided by capital T. Here the capital T is the sampling period. So by after substituting and simplifying your equation, we will get our h of z. That is nothing but the transfer function of our digital filter using the approximation of derivative method. And coming to the impulse invariant procedure, you have to express your h of s in this pattern, right? Summation term. So using the partial fraction expansion procedure, we can express our h of s equation in this way, right? That is the sum of single pole filter. Here the P is nothing but the pole of the filter and C is the constant. So here the K varies from 1 to capital N. So 1, P1, pole number 1, P2, pole number 2. Likewise, we will have. So depending upon our value S minus S1, that is S minus, for example, if I am having my data as 2 divided by S minus 2 plus 3 divided by s minus 5. So in this case, 2 is my pole location, first pole location, and 5 is my second pole location. That is the meaning, right? And the numerator values 2 and 5 are the constants. So likewise, using the partial fraction expansion procedure, we can able to express our h of s equation in this pattern, summation pattern. After finding this, right, you can able to find your ck and your pk values. That is different pole locations and your different constants, corresponding constants. So you, after finding this, you can able to write your digital filter transfer function. H of z is equal to summation over k ranging from 1 to n, ck divided by 1 minus e to the power p into k. This product p into pk into t is available with the e to the power, right, into z to the power minus 1. This z power minus 1 is not in the power of e. So only the terms pk into t is in the power of e. So pk is, for example, if I am having k is equal to 1, then c1 divided by whatever value I am having for c1, that should be substituted here, divided by 1 minus e to the power p1, what value we are having for pole number 1, into t, capital T. Again here t is a sampling period, and into z power minus 1 plus c2 divided by something like 1 minus e to the power p2 into t into z power minus 1. Likewise, we will expand our equation for obtaining our h of z equation.